Welcome to the CS Classroom. This is Artificial Intelligence for the A-Level Computer Science exam. In this tutorial, we will cover all of the content you need to tackle any AI-related questions on the exam. However, this isn't a huge component of the A-Level syllabus or exam. In fact, this is generally just going to be one 5 to 7 point question on paper 3, usually a multi-part question. However, in my opinion, this is not one of the more difficult topics, so it's more like low-hanging fruit. Hence, I recommend you watch this tutorial so that you can maximize your exam score. Now we're going to start off by talking about AI and types of AI. Basically what AI is AI is a computer-based system that tries to solve problems by simulating how the human brain works and how humans learn. Now, a subset of AI that we're going to be focusing on is machine learning. So if I am using the term machine learning, I'm still referring to AI or artificial intelligence. Now, there are 4 types of AI that we're going to be talking about: supervised learning, unsupervised learning, reinforcement learning, and deep learning. Now, we'll also be learning about something called neural networks, which works behind the scenes of supervised learning and deep learning. More on that in a second. Now, the first thing we want to learn about is supervised learning. And actually, I would say before we learn about supervised learning, I just want to explain how this whole machine learning thing works to begin with. So generally what's going to happen is, as I said, with machine learning, we are attempting to make a prediction, or we're attempting to get some output based on some input. This may be a prediction, this may be a classification of an image or text according to certain categories. This may also just be a situation in which we need to learn what the best path is through a series of obstacles. For example, an AI attempting to play chess or find its way through a maze. The point is we have some input, and based on that input, we want to be able to get some output, either based on past behavior or some other data. So what we're going to be doing is putting in some input data into an AI model. We'll call this a model, and then getting some output. Now, this model is a combination of algorithms and data. So in certain cases, we can actually teach this model to give us a certain output based on a certain input. In other situations, it'll be working on its own to find patterns in our data and then classify them accordingly, or give us output accordingly. Now, with supervised learning, we can basically teach our machine learning model based on past experience. So this is maybe a bit complex. We'll come to this image later. But in this example, the way our machine learning model in supervised learning works is we should be able to put in images of animals. And based on those images, the machine learning model should be able to decide whether each image represents a cat or not. Now, in supervised learning, what we're going to do first is something called training. So we're going to teach this model to be able to recognize a cat. And what we're going to do is in order to train it, we're going to give it data with labels. So we will give the machine learning model a series of images, and each image will have a label, a text label attached to it. That label will signify whether or not it is a cat. So that way, the machine learning model can change its collection of data and algorithms in order to be able to then recognize an image of a cat without having the label. Basically, we show the model an image of a cat, we tell the model that it is a cat, and we do that a bunch of times. So we do that, maybe a couple of 100 times. That way the model can actually learn what a cat looks like, so that when we give the model images that don't have labels, images of all kinds of animals, it can pick out what the cats are. That process of training is what signifies supervised learning. Now, next we have something called unsupervised learning. So with supervised learning generally, we were able to perform tasks like classification. In our example, we talked about classifying images of cats, But we could also do things like classifying spam emails as opposed to regular emails. We could analyze images and break down people by race. We can do all sorts of things, really. Now, while supervised learning operated on past data, unsupervised learning doesn't really require any training at all. It just takes any set of data that doesn't have any labels, and then it kind of analyzes it on its own and then separates it into different categories. Now, the algorithm doesn't know what categories they are. It just knows that these things are different. So basically, you can think of it as something that just takes in a bunch of data and then tries to figure out what's different about them, and then outputs groups of different things without labels. Then it's up to us to figure out what those groups signify, like what is unique about each of those groups. For example, after the unsupervised learning model or algorithm outputs its result, we would then add a label: rectangles, circles, triangles, hexagons, and so forth. So with supervised learning, we had some sort of training where we trained the algorithm, we gave it known data, right? So we gave it data with labels and we trained the algorithm. Unsupervised learning, we just give it a bunch of data and then it just puts it into different buckets. Now, again, to kind of talk a bit about the difference between supervised learning and unsupervised learning. With supervised learning, we're typically going to be doing classification tasks like dividing socks by color, or even identity fraud detection. We could put in some data for sets of information that are fraudulent and those that aren't. So then our supervised learning algorithm can distinguish between the two. We might also do things like market forecasting, so making predictions based on some past empirical data. Now with unsupervised learning, we're not really doing much prediction. We're just kind of separating things based on patterns or based on their structure. So we might separate customers based on their behavior into different buckets. That can also inform how we conduct marketing. But the point is that we are, in supervised learning, we're inputting pre-categorized data, labeled data. Unsupervised learning, we're inputting unlabeled data. In supervised learning, we're getting some prediction. In unsupervised learning, we are just getting, our result is going to be the data that we input, but just separated into different buckets, which it's then up to us to label. Now, the next type of learning we're going to go over is going to be reinforcement learning. So reinforcement learning is similar to supervised learning, except the model is being trained in real time. So think about a mouse going through a maze and then getting sugar whenever it gets to the end. That's an example of reinforcement learning. Now, to clarify that, let's go ahead and let's look at an example. So right here, we have a robot that theoretically needs to make its way to the diamond. So as this robot goes through this maze, it can detect different things. So it can detect fire and perhaps other obstacles. So what we could do is we would have a computer program that is going through a digital maze, right? And this computer program is going to have some sort of point system. So maybe it starts at 0 points. So what we would do is we would have this computer program try all different paths. So for example, it might go here and then try to go here. It might go here and then try to go here. It might go here and then, or just straight. However, our algorithm is going to have a reward system. So when we hit the fire, we might tell our algorithm to give us negative points. When we do successfully move a square forward without going to the fire, it might be +1. When we hit the diamond, it's obviously going to be like +20 or something like that. So the point is, with reinforcement learning, we're basically trying a bunch of different tasks. And when we do those tasks and we achieve a desired result, we're going to reward our algorithm. When we don't get a desired result, we're going to, I guess, punish our algorithm with negative point count, for example. So that way, our algorithm can learn the behavior that's required to complete the task that we want it to. It's basically like teaching a child based on a system of punishment, right? Like a child breaks your favorite vase and you give them a timeout. A child gets an A, you give them candy. It's the same thing, but on an algorithmic level. And this is in a lot of ways how, for example, you could train algorithms to play chess, to work its way through a maze, or really to complete any task where there are a bunch of different possible tasks, or there are a bunch of different possible paths, and we actually don't even know what the best one is, but we want our algorithm to figure it out and get to the end, and then to be able to replicate that behavior over and over again. So really, when you talk about algorithms learning by making mistakes, I guess another good example is when we see robots doing different things and then learning from their mistakes and adapting. That's an example of reinforcement learning. This is basically what we just talked about. Now, I kept talking about this robot in the maze. That's actually called an agent. It's like, I guess, an entity that's being rewarded, or an entity that's moving around in an environment with a series of rewards and penalties. But it's basically adaptive learning. And we just keep iterating until the algorithm or until the agent knows the best way to accomplish the task that we want it to, with the highest reward and with the least punishment. So the highest point count. Okay, so now what we've got right here is an A-level exam question. We're actually not going to complete this question, but what I do want to do is answer the questions based on what we already know. So we learned about supervised learning, reinforcement learning, and unsupervised learning. So I want to look through these descriptions and then match them up with the appropriate definitions. Once we go through deep learning, we'll return to this question and examine it again. Now, first we have supervised learning. Now, if we look at some of these descriptions, this is going to be the best answer. So supervised learning enables learning by mapping an input to an output based on example input-output pairs. So what this is talking about is, so basically with supervised learning, remember we talked about training the model first with data with labels? Those are input-output pairs. So the algorithm or the model learns based on historical data or past data that has the input with the corresponding output. And then based on that, it can make predictions as to what the output for a given input should be. Next, we have reinforcement learning. So reinforcement learning is best described as enabling learning in an interactive environment by trial or error using its own experiences. So this is basically a description of that whole maze we were talking about and the reward and punishment system. Next, unsupervised learning enables learning by allowing the process to discover patterns on its own that were previously undetected. So with unsupervised learning, we are basically just detecting patterns, and then after that, we'll have to classify them based on what we see. Deep learning is what we still need to cover, and now we're going to take a look at that and then return to this question afterwards. So the foundation of deep learning is something called neural networks, which is also referred to as artificial neural networks on the A-level exam. Now, neural networks are actually meant to simulate the system of neurons that exists in our brain. However, the way that we look at it in algorithm, while an analog could be our actual neurons, it's really organized in a much more simplistic format. In every neural network, we're going to have an input layer right here. We're going to have some hidden layers, and then we're going to have an output layer. Now, a neural network is what's behind supervised learning and deep learning, which we'll talk about in a moment. Now, if we go back to our cat example, right? Remember we were talking about how we're putting in images of cats with labels, and then we're getting, eventually we should be able to predict whether an image contains a cat or not. Now, what our input layer is going to do is our input layer is actually going to accept images of cats. So each time we want to input an image, it's going to go through a neuron in our input layer. Now, once it goes into our input layer, it's going to be sent out to every single neuron in our hidden layer. And then from each one of those neurons, it's going to be sent to every single neuron in the subsequent layer until we get to the output layer. And the output layer is where we're actually going to get cat. It's actually where we're going to get our answer. So we're basically putting in our data into our input layer. We're doing the processing in the hidden layer. And then our output layer is what's going to give us the answer. Now, we're going to talk a little bit more in depth on this hidden layer. But basically, the way this is going to work is that initially, when we train our neural network, we're going to be putting in data with our label to the input layer. And then we'll get through do all the processing on our hidden layer, and then we'll get to our output layer. And based on our output from the output layer, so if we get the wrong output, then we're going to go back and we're going to change some things about these hidden layers. So these hidden layers aren't like static things. We change these hidden layers based on our training so that we can then get the desired output based on the equivalent input. Now, what that means, let's talk a little bit more about that. So I think what I'm going to do is we're going to talk about an example of detecting email spam. And based on the example, I'll explain more about how neural networks work. Now, the object behind this real-world scenario to explain neural networks is to create a system that allows us to distinguish between spam email and normal email. We're not actually going to write code, but I'm just going to use this as a way to explain how neural networks work. Okay, so how this works is we're going to have some text in our email. So we have a spam email. And the best way to understand how a neural network works is to think about how we analyze an email to figure out whether it's spam or not. So when we look at an email, we're looking for certain keywords, right? So we're looking at things like discount, maybe like % off, free, act now, things that sound really gimmicky. Now, for us, it's pretty clear. We pretty much know what we're looking for, either consciously or subconsciously. However, we need to teach those same things to our neural network. Now, in order to show you how that works, we're going to follow our email through our neural network as it's being trained. So remember with supervised learning, we're starting with a training process. So what we're effectively going to be doing is we're going to be putting our spam email through our neural network, and then we're going to be seeing how it does. And based on whether our neural network correctly outputs that it's spam or not, we're going to be changing our neurons in our hidden layer. Now, what we're going to do first is we'll take our email. We're going to take all the text of our email and put it into our input layer. Now, from our input layer, all the text is going to go to each of these neurons. So all the text of the email will go to this neuron, this neuron, this neuron, and this neuron right here. Now, what's important to note is that each of these neurons represent a particular word that we're looking for in a spam email specifically. This might be like discount. This one might be like 50% off. This one might be like % off. And this one may be, this one may be act. And that's not just going to be our first layer. All of our hidden layers are going to basically be doing the same thing. So each of them will have a particular word or phrase that matches a spam email corresponding to each neuron. So for example, right here, it may be like sign up or something like that. Now the idea is that each neuron has a weight, and it has something called an activation function. So basically, what's going to happen, let's say that we put the spam email in, and then it hits this discount neuron. Basically, that discount neuron, it's going to output something closer to a 1 as opposed to a 0. Now, if it has 50%, it's probably going to output a 1. If it doesn't have % off, it's going to output a 0. If it doesn't have act, it's going to output a 0. So basically, these neurons are each going to send some sort of signal based on whether the word that corresponds to that neuron is contained in the email or not. And then we're going to pass the text So we're going to pass our signal, so our 110, from each neuron, along with our text, to every single other neuron in the next layer. And we're going to repeat that process. Now, when we get to the end, if this is really a spam email, then we should get spam. In that case, we're not going to change our hidden layers. But if we get it wrong and it says not spam, then we're going to adjust some of these layers, particularly those that return to 1. Because if we got not spam, we should be getting spam. That means our neurons that successfully detected a word in a spam email should have a greater weight. So that means that we might have something like 2. So that means that each of these neurons, these ones that were lit up that had 1, will count for more. So they'll end up counting for 3 or 4, depending on our training algorithm. So this process of adjusting weights to give our neurons more importance is called backpropagation. So eventually we're going to change the weights in our neural network so that those neurons that are more important for detecting spam have more importance and more influence over our final result than those that are not. And that's essentially how a neural network works. We have weights, and these weights are basically how influential each neuron is. Now the activation function basically takes, it's basically responsible for taking our result in our neuron and then turning it into a specific numerical value that we can send on to other neurons, and that results in our output. So the activation function is really about kind of wrapping our result up in a numerical value that we can then use to effectively calculate whether we have a spam email or not a spam email. And the weight is responsible for how influential each of our neurons is. But at the end of the day, what I want to highlight is that each neuron represents a particular characteristic of our spam email, and each time the word for a specific neuron matches something in the spam email, that neuron lights up and sends a positive signal. And based on that signal, combined with our activation function, when we get to the end, we can make a prediction as to whether they're spam or not. So after we put a bunch of data in with labels, our weights are going to change. So that means that every result that goes through here might give us a 5. Every result that goes through here might give us a 1. Every result that goes through here might give us a -1. And the weights of all these neurons, how influential they are, is going to change throughout training. So that way, once we put in an email that doesn't have a label, that we don't know to be spam or not spam, we'll get spam. We'll get a correct result at the end. And that's basically how neural networks work. So just to kind of summarize, our input layers accept data. Our hidden layers are responsible for deciding what the output should be based on our input. And it's also where training occurs. And then our output layers output the final prediction, in our scenario, whether it's spam or not. Now, this could very easily work for images as well, except in the case of images, we'd be breaking down our image into pixels, inputting those into our input layer, and then we would most likely have neurons that are trying to detect either collections of pixels, so patterns of pixels, or the presence of individual pixels. But the concept remains the same. Now, if you want to know more about how this neural network works in depth, I did actually write a description here, but it's quite dense, so I didn't really want to go through it word by word. I felt like a diagram was a better way to illustrate it. Now, let's take a look at some A-level questions to get a better understanding of neural networks, particularly from the exam perspective. So the question here is, state the reason for having multiple hidden layers in an artificial neural network. Now, in our spam example, each neuron represented a particular word or phrase that might correspond to spam in an email. So that means that the more neurons that we had, the more likely we were able to detect a spam email, and the more accurately we were able to detect it, because we can effectively look for more data points that correspond to a spam email. So it turns out the reason we might use more hidden layers is if we're trying to solve a problem that has a higher level of complexity. So if we have more data points that we want to look at, image recognition is a great example, particularly if we're looking for something very specific. Moreover, if, for example, in our spam email, we were able to look for more words that correspond to spam instead of less, then we'd also be able to improve the accuracy of our result. It's just a question of looking at our input data with more granularity. So we can solve more complex problems and we can improve the accuracy of our result. And ultimately that helps the neural network to learn and make decisions on its own. Although this is kind of like a weird answer. I mean, this is just like a really this is not a specific answer, I feel, to the question. The other thing we have here is, the other reference we have is to deep learning. Now we haven't talked about deep learning yet, but if you go to deep learning, so deep learning is basically a form of supervised learning, but it just has many more hidden layers than the average neural network. So it's supervised learning. With some of the example neural networks we saw, we had two hidden layers of neurons. Now with deep learning, we're going to have many more hidden layers to be able to analyze more complex problems. And this is also meant to simulate the human brain, because the human brain is more similar to a neural network with, for example, hundreds of hidden layers rather than just two. So the main difference between deep learning and just regular supervised learning, both of which make use of neural networks, is just that deep learning has many more hidden layers. Now, I want to go back to one more question, which I think is a great summary of neural networks in general. This question is, explain how artificial neural networks enable machine learning. Now, some of the answers are that they replicate the way the human brain works. Weights and values are assigned for each connection between nodes. Now, nodes is referring to neurons in our neural network. Now here it says that they're assigned for each connection. So that means the link from one hidden layer to another. I would argue that actually there's different ways to define this. Probably for the A-level exam, it's better to say that the weights are assigned to each connection. The data are input at the input layer and passed into the system. So they're analyzed by each subsequent hidden layer. The process of training is repeated many times until we get the optimum output. So this is that backpropagation we're talking about, where we're adjusting weights. Decisions can be made without being specifically programmed. That's the whole point of neural networks. We do have an actual reference to backpropagation here. And here it says backpropagation of errors will be used to correct any errors that have been made. So this is where we're changing weights. We're changing the characteristics of the hidden layers in order to respond to errors in prediction. We have the output layer provides the result. So basically in this question, if you describe an artificial neural network as we did, then you would be able to probably knock out the 4 points required. So we'll talk a little bit more about we'll look at some deep learning A-level questions, describe what is meant by deep learning. So uses artificial neural networks, contains a high number of hidden layers. We can say it's a specialized form of machine learning, and it can extract higher level features, maybe solve more complex problems. Outline the reasons for using deep learning, makes good use of unstructured data, can outperform other methods if the data size is large. We can process data with a nonlinear approach. This has to do with that activation function that we talked about earlier. So that activation function allows us to take our results and then modify them in a way that's not linear. So this is as opposed to doing something like this. I guess this is particularly more important when we're talking about making numerical predictions. This means that we're not just going to be doing a linear regression to predict data. We're going to be looking at data non-linearly so we can make more perhaps accurate predictions, particularly in working with numerical data. Deep learning is also effective at identifying hidden patterns, and more so than humans. And we can have a more accurate outcome with higher numbers of hidden layers. So it does better when data sets are large. We can use a nonlinear approach, especially when predicting numerical data. It makes it easier to identify patterns that won't be visible to humans. And with a higher number of hidden layers, we can get a more accurate outcome. Okay, so the first shortest path algorithm we're going to look like is going to be Dijkstra's algorithm, as it's actually called. Now, generally, shortest path algorithms allow us to find the shortest path from one point in a network to another point. So from one node or one vertex to another vertex. And we'll see what that looks like in a moment in a graph. So with Dijkstra's algorithm, we want to find, basically Dijkstra's algorithm allows us to most efficiently find the path from one point to another point. And when we see it on the A-level exam, we're going to be solving problems like this. Calculate the shortest distance between the base and each of the other towns in the diagram using Dijkstra's algorithm. So basically, to illustrate how this algorithm works, I'm just going to go ahead and solve this problem. Now we're starting at the base right here, and we need to find the distance to each of these 6 towns. And these numbers, like 5 for example, represents the distance from the base to each town. So what we're going to do is we'll start with the distance from the base to town 1. And we need to look at all the possible paths because that's what Dijkstra's algorithm is going to do. So if we go directly from base, to town 1, the distance is 4. Okay? But we have other ways to get to town 1. We could go from base to town 3, and then from town 3 to town 1. And then together we'd have a distance of 2 and 1, which adds up to 3. So our shortest path is actually going to be 3. Next, if we want to get to town 2, we have a couple options. So we could go directly from the base to town 2, which would be a distance of 5. We could go through town 3 and 5, which would give us 6. And I think that's kind of about it. I don't really see any other way. So probably your distance is just going to be 5. The next thing is we have town 3. Now, to get to town 3, we could go through town 1, which would give us a distance of 5, because 4 plus 1 is 5. Or we could just go straight there, which is a distance of 2, so we'll just stick with 2. For town 4, we have a couple options. We can go through town 1, which is going to be 4 plus, let's use a different color. That's going to be 4 plus 7, which is going to be 11. Or we could go through town 3 and town 1, which is going to be, or town 3, town 5, town 3 and town 5. So we'll have 2 plus 1 is 3, plus 6 is 9, which is less than 11. So probably you want to stick with 9 for that one. Now to get to town 5, I think it's pretty simple. We're just going to go through town 3 from the base. So we're going to have 2 plus 1, which is just going to be 3 to get to town 5. And then to get to town 6, we have a few options. We can go from the base through town 2, which would give us 13, 5 plus 8. We could go from the base to town 3 to town 5 to town 6. And that's going to give us 2 plus 1 plus 5, which will give us 8. We could also go, let's see, 3, I guess we could go through town 3, town 5, and then town 2 to get to town 6. But that would just give us like 2 plus 1 plus 3 plus 3 plus 8, which is like 5 plus 1, 6, 14. So probably our answer there is 8. So basically it's really just about finding the shortest distance, even if that means going through different towns or going through multiple towns as opposed to just one town. And let's see if we got that right. And I think we did. 352, 938. Perfect. And that's basically how you solve a Dijkstra's algorithm problem. And that's what you're going to see on the exam. Now, the next type of algorithm we want to look at is going to be the A-star algorithm, which is similar to Dijkstra's algorithm with one difference. So we still have these distances, but we also have something around, so we have these distances right here, which is represented by G. So I'm just going to circle these in red for our distances. But then we also have something called a heuristic. And the heuristic is the predicted distance to our destination at each node. So for example, if we go from home to, A, okay, that's distance of 1. But then we have an h equals 10. So our projected distance to the school, actually, if I didn't make it clear in this particular question, we want to go from our home to our school, our home node to our school node. So basically, this looks like Dijkstra's algorithm, But if we go from home to A, we know our distance from home to A is going to be 1. But then we have h equals 10. So our projected distance from the home to the school via node A is going to be 11. Basically, h tells us our projected distance to our destination, which is our school, from any given town. So our projected distance from our home to our school is going to be 14. Our projected distance from node B to our school is going to be 7, etc. So we're going to make decisions on how to proceed through this diagram based on our, not necessarily based on the actual distance, but by first figuring out the minimal projected distance and then going from there. So basically what we need to do is we need to fill out this chart. So what we need to do first is we need to find, we're going to go to only the first towns away from our home. So we just want to go to the towns that are next to our home and then figure out what the shortest projected distance is. So if we go from home, so let's say we go from home to A, okay? That means that our projected distance is going to be 11. If we go from home to C, that means our projected distance, we're going to have a real distance from home to C, which is 4, plus our projected distance right here. So we're going to have 4 plus 9 is 13. And if we want to go from our home to B, which is the next other town that's next, we're going to have our real distance from home to B, which is 5, and then our projected distance from B to the school, which is going to be 12. Okay, so we're adding a real distance from our home to our next town, and then we're adding that to our projected distance from that next town to the school to figure out what the minimal path is. And that looks like A. So in this chart, we need to fill this in. We have 11 right here. To node B, we're going to have the cost from home node was to B was 5. That's the G, that's the actual cost. And our heuristic, which is what our projected distance was at B, is 7. So we're going to write 7 right here, and we're going to have 12 as our total. And then for C, our cost from our home to node C was actually 4. And then our heuristic there, so our predicted distance to this school is 9. So we're going to fill it out, and we're going to get 13. So we need to write all of these things down in this chart they gave us. And now that we've done this, we need to figure out what is the lowest total. So what is the lowest projected distance overall from our home to any one of these nodes? And that's A. So because that's A, we now know that we need to go through A to get to our destination, to our school. So we need to see everywhere we can go through A from our home. So from A, we really have a couple of options. You can go from A. So basically now we're looking at the secondary nodes, right? So we can go from A to B, and then from B to the school. So now if we go through A and B to get to the school, we're going to get our total, we're going to add up the real distance from home to A, which is 1. So we'll say so now we're going to say from A to B. So home to A to B. We're going to add up our real distance from home to A, which is 1. Our real distance from A to B, which is 3. And then our heuristic, or our projected distance from B to the school, which is 7. So we're going to do 1 plus 3 plus 7, which is equal to 11. And then the next thing we're going to do is, let's see, is that right? Yeah, we have 1 plus 3 plus 11. Okay, so the next thing we're going to do is we're going to try another alternative. So we're going to try going from our home to A to E. Now from home to A we have 1, and then from A to E we have 6. So from home to A we have 1, from A to E we have 6. And then our projected distance from e to the school is 3. That's 3 right here. So you have 1 plus 6 plus 3, which is going to be 10. Those are only real options, like as far as secondary nodes go through A. So right now, so what we're going to do is we're going to write B right here. The cost from the home node was, that was like 1 plus 3. So our actual cost, that was 1 plus 3. And then the heuristic was actually, what was that? That was 7. And that ends up 11. But then we also go to E right here, right? That was our second like sort of path. And there we had 1 plus 6 for the distance from our home node. And then we added on for our heuristic, we added on 3. So we basically had 7 plus 3 is 10. So given that our path from A to E is the minimal path at this moment, we're going to go from here. So we're going to start right here. And then we have 2 ways to get from there to the school, which is our ultimate destination. We can go through node F. So if you think about going from the home, so now we have, I'll just give you another color. We have our home to A, to E, to F. So we're going to add up our actual distance from A to E to F, and then on top of that, add our heuristic from F to the school. So we're going to do 1 plus 6 plus 1. So 1 plus 6 plus 1, and then we're going to add our heuristic, which is 3, and that gives us a cost to get from home to the school via A, E, and F. So 7 plus 1 is 8, plus 3 equals 11. Then our other path is to go straight from E to the school. And that's actually just like, we know what the cost of that's going to be. Like we don't have another node. So we can say home to A to E to school is going to be equal to, it's going to be 1 plus 6, 1 plus 6 plus 5, which is going to be 12 actually. So right here we have 11. On the other hand, here we have 12. So right here, we're just going to write F, and we can say, let's see, yeah. So we're going to say 1 plus 6 plus 1, 1 plus 6 plus 1, and our heuristic from there was 3. So that's going to give us a solid, let's see, 7 plus 8, 11. And then we also just had, we're going straight to the school, right? So let's type school right there. And that was just going to be like 1 plus 6 plus 5 with no heuristic, which is going to give us 12. So that means that our final path is going to be from home to A to E to F and then to the school. And this right here is 1 point. And then our work in our chart is actually going to be worth 4 points. So right here, we almost got all of it, but there are a few things. So we need to have 1 mark for each of these calculations. So our first one is just going to be B, which is going to be line, I'm just going to go ahead and mark which ones we got right and which ones we didn't. That's going to be on line 3 right here. And then our next one is going to be C, which is on line 4, so that's another point. Next one is going to be from B to E on lines 5 and 6, so B and E on lines 5 to 6, so these calculations right here. Next we have from F to school, so that's going to be these 2 right here. So we have node F and node school. And then I guess the last one we actually need to do, which we left out, is that's like really our final calculation. So that's not including the heuristic, because right here we included the heuristic when we were making our calculation from A to E to F. But we need to do the real calculation, which is just going to be 1 plus 6 plus 1 plus 3, because here the heuristic was the same as the actual distance. And that's going to give us our 12. And that's going to be our last point right there. Those are our 4 points. Now, actually, the order does matter for points, which we nailed. But yeah, I guess the one thing that we missed was just the last and final calculation. And then if this is a 5-point question, we get 4 points for our table and then 5 points for writing our path. And this is our path right here, which we also got right. So anyways, that's actually it for shortest path algorithms. You basically, particularly, I think the Dijkstra's algorithm was the easiest. The A-star algorithm is not so complex, but you just need to be taking into our projected lengths from each node, which is also known as the heuristic. And hopefully that explanation kind of cleared up how we'd work through these kinds of problems. Now, one last thing we're going to cover, which we kind of already talked about, was the concept of graphs. So not only our neural network, but also the diagrams we saw for our Dijkstra's algorithm and the A-star algorithm are all graphs. And when we're talking about graphs, it's important to refer to these as nodes or vertices, vertex for singular. Now, these are used to visualize paths, both through neural networks and paths for our shortest path algorithms. And we use graphs not only to represent these in a clear way, but also because oftentimes we can use graphs in the form of linked lists or other such data structures so that they can be processed by algorithms. So it's a format for storing data as well, such that they can be processed by algorithms that are used to perform something on them. Now, right here we have a question explaining the use of graphs to aid artificial intelligence. And this is an important question because we mainly covered graphs in the context of shortest path algorithms. And so we can say that artificial neural networks can be represented using graphs. They can provide a structure for relationships between nodes, such as like the hidden layers, the initial layer, and the final layer. AI problems can be solved as finding a path in a graph, like our shortest path problem, which is technically an AI problem. They can be ingested or analyzed by a range of algorithms. And I guess an example of this would be backpropagation, where we're actually going back into a network algorithmically, and we're changing certain characteristics for each node or neuron, which is the weights, which we can say is at those neurons or at those nodes. Okay, so that is about it for AI. One thing I did want to cover before I let you guys go is my machine learning course. So this is just kind of a quick intro to machine learning for the A-level exam, but I'm actually planning on creating a whole machine learning course for high schoolers who may be interested in getting into data science or AI in university. If this seems like something that's of interest to you, then please click on the link in the description to subscribe to my online store, and you'll get a notification when this course is out. I'm not going to spam you. I very rarely send emails to these links, but this is just in case you're interested. Anyways, if you found value in this video, please remember to like the video and go ahead and subscribe to the channel for future videos on A-level computer science in preparation for the exam. Have a nice day.